Ladies and gentlemen, welcome to my presentation on mathematicians' greatest mistakes. Yes, they do make them, and even at the highest level. It is not unusual for mathematicians to say words like, "That is what the mathematics tells us, so it must be right." If only that was true. Unfortunately, it isn't. This indicates my mathematics and physics capabilities to pass such comments. In this presentation, a mistake is the difference between what is experimentally observed and what the mathematicians predict. The leading contender with a mistake that can probably never be exceeded is the Big Bang theory for the formation of the universe. Forwarded by mathematicians who call themselves theoretical cosmologists, it goes something like this. In the beginning there was something, or nothing, we don't know yet. It exploded in a big bang, starting space and time. Along the way it broke known physical laws. About 13.8 billion years later, Earth-bound astronomers observed it and measured its properties in reasonable detail. To explain what was observed and measured, theoretical cosmologists decided they needed 24 times the mass and energy that astronomers observed to give the universe a 1 in 10 to the 60 chance of existing. The mathematician's choice is the Big Bang. They will tell you their mathematics is soundly based on Einstein's general relativity theory, so it must be right. A brief glance at his 1916 paper on the foundations of the general theory of relativity soon verifies Einstein's maths were complex. But furthermore, it made predictions that matched observation. How can mere mortals argue against those with mathematical knowledge of such complexity? At that stage, most people put it in the too hard basket. They don't have the mathematical skills to contest the work of those mathematicians, or so they think. To counter that, this presentation is divided into 3 episodes. The first deals with Einstein's gravity and its solutions. The complexities of Einstein's maths seems to make it difficult for mere mortals to question them. To show how easy Einstein's gravity really is, I derived 2 full gravity field equations from his work on gravity. Their derivation and use are nothing more complex than mid-undergraduate mathematics. Even some good high school matriculants could find it easy to solve these simple yet accurate gravity field equations. Yes, gravity is that simple. Einstein made it seem complicated. The second episode deals with all the astronomers' observations that theoretical cosmologists say can only be explained under their expanding universe calculations and theory. It will be shown that under a steady-state universe, they all have simple physical explanations that give a better match with observation. The third episode deals with dark energy and dark matter that mathematicians insist are necessary to explain astronomers' observations. At the end, all we are left with is what the astronomers observe, and that is all that is needed to explain their observations in an infinite steady-state universe. This presentation needs some maths knowledge to understand it. To those who just want to be entertained, they'll find quite a lot as they see the simple mistakes the experts made. To show I'm not cheating, I'm going to display some information written by others, particularly Einstein. Unless otherwise stated, all quotations used will be copied from this book. This page is from his 1905 paper, "Does the inertia of a body depend upon its energy content?" Note the 2 highlighted regions. If a body gives off energy L in the form of radiation, its mass diminishes by L over c squared. If theory corresponds to facts, radiation conveys inertia between emitting and absorbing bodies. Those extracts show Einstein considered that photons had mass. Despite that, later mathematicians treated all photons as massless particles. Ignoring Einstein's work was a big contributor to their greatest mistake. Next we go to his 1911 paper on gravitation and light. In it he applied Newtonian gravity, which he expressed as phi, to photons that he had previously determined had mass. He considered the height difference of photons rising from S1 to S2 against gravity. In a few simple calculations, he showed photon frequency decreased with height as photons lost kinetic energy and gained potential energy. He calculated that photons would be redshifted by 2 times 10 to the minus 6 when they traveled from the sun's surface to Earth. That was already known. And that should have been another wake-up call to all those mathematicians who believed photons were massless. It wasn't. What surprised me was that no one attempted to expand on his 1911 paper, myself in 2021 excluded. Anyone interested can see this United Kingdom Institute of Physics Journal of Physics Communication published at either of these addresses. That expansion involves rearranging terms and early undergraduate calculus. This is about as complex as it gets. It changes Newton's inverse square law to this GR, or gravity redshift term, of GR equals GM over R times 1 plus Z all squared, and that equals GM over R squared e to the alpha over R, where alpha equals 2gm over c squared. It shows that Newtonian distances, Rn, become relativistic distances. Rel equals Rn times 1 plus z, or Rn times e to the alpha over 2r. Newtonian time becomes relativistic time, Trel equals Tn over 1 plus z. If the wavelength increases, that is, the photons are redshifted, the distance increases. This paper shows that Einstein's space-time distortion to produce gravity was simply photon redshift z. It will be shown later that this matches all known gravity properties. That is not difficult. It could have been done by anyone after 1911. It wasn't. So we have to continue down the path Einstein took. In 1904, Lorentz had already worked out the special relativity corrections for distance and time with constant velocity between an observer and observed. In 1905, Einstein called that correction factor beta, the square root of 1 minus v squared over c squared. He extended the equations to the variations with mass, shown on the top of page 63, and energy, bottom of page 63. As a side issue, it is worth noting his different use of beta. In longitudinal mass, he derived beta cubed. In transverse mass, he derived beta squared. For changes in energy, he just used beta. I have no idea what the difference between longitude and transverse mass were. No wonder his work was confusing. It was soon realized that mass m of an electron at velocity v was given by mv equals m naught divided by beta equals m naught over the square root of 1 minus v squared over c squared, where m naught is the rest mass of the electron. It applies for any other particle. He later realized that the relationship between energy and mass was given by E equals mc squared. Einstein calculated that for electrons. In slide 5, I showed that he indicated photons had mass. Mathematicians assumed that that equation also applied to photons. Therefore, when traveling at the speed of light, they should have infinite mass. They assumed Einstein was wrong and used photons as massless particles in their calculations. A bit of common sense physics, supported by simple maths, shows the corrections only applies to particles. It does not apply to photons. They can only travel at c and will have mass mp equals h nu over c squared. the mathematicians continued their mistake. Michelson and Morley measured the speed of light was constant no matter which direction it was traveling around the sun. Einstein realized that meant there was no absolute reference frame. All measurements were relative to the observer and the observed. He referred to those corrections as special relativity. They applied only to the special situation in which the observer and observed moved at a fixed velocity relative to each other. Einstein was not satisfied with just the special relativity corrections. He wanted to work out the relationship of the general situation in which two bodies were accelerating with respect to each other. That was what he attempted in his 1916 paper on the foundations of the general theory of relativity. He needed to use tensors for that approach, and they were simply vectors in four-dimensional space. But it is worth noting this extract from his foundations paper. It is not my purpose in this discussion to represent the general theory of relativity as a system that is as simple and logical as possible and with the minimum number of axioms. But my main object is to develop this theory in such a way that the reader will feel that the path we have entered upon is psychologically the natural one, and that the underlying assumptions will seem to have the highest possible degree of security. Well, he certainly fulfilled the first part. His paper was not as simple and logical as possible. He did not fulfill the second part. Nobody understood the path he took. If they did, they would never have allowed mathematicians to make their greatest mistake. It is my impression that quotation served its purpose of intimidating readers into thinking he was a brilliant mathematician. Many have tried to understand or follow his mathematics. Despite their pretense, they all failed. So that you will have a better understanding, I'm going to mention a couple of important points and then show you how easy it is to solve his gravity theory. Going through his paper, he started trying to solve the general situation of accelerating bodies, including those traveling in curved paths. Page 122 is his usual style, namely complex maths that are difficult to follow. And that was nothing unusual for Einstein. But as he went through it, he began to get somewhat confused. Although he had previously introduced gravity, Section 8 suggests that he found a way out of that confusion by introducing this standard multidimensional differential equation. He applied it to the four gravity tensors, g, mu, nu. Those g terms are nothing more than the gravity terms in the four dimensions, x, y, and z for space, and t for time. That enabled him to move relatively smoothly from his general relativity theory to its only useful application, namely gravity. After another 17 pages and a mixture of other tensors, he derived his gravitational field equations. The square root of minus g equals 1 means gravity is only attractive. The important feature is the highlighted section below. It must be pointed out there is only a minimum of arbitrariness in the choice of these equations. In that, he was saying equation 47 was an approximation. That also applies to all other forms of his field equations. See, for example, 47a. As every good mathematician will tell you, an exact solution to an approximation is always an approximation to reality. Mathematicians continued their merry way of deriving variations of Einstein's gravity field equations. Here are some examples. The elite claim to be able to solve them and get this answer, the accepted Schwarzschild metric. Being astute mathematicians, they worked out this meant gravity was stronger than Newton's inverse square law. In his 1687 Principia, Newton worked out that if gravity was inverse square, a planet orbiting the Sun would traverse an ellipse in which its perihelion position would always be at the same point, as in A. Kepler had come to the same conclusion earlier. Newton also worked out that if gravity was stronger than inverse square, a planet would orbit a little closer to the Sun and travel a little faster. It would return to its perihelion position a little earlier in each orbit. That would mean its perihelion position would regress against its travel direction, as shown in B. Conversely, if gravity was weaker than inverse square, a planet would orbit a little further away from the Sun and travel at a slower speed. It would take longer to return to its perihelion position, which would precess in its direction of travel. It was known in the late 19th century that Mercury's orbit precessed in its orbital direction by about 43 arcseconds per century. That should have been a wake-up call to those mathematicians who solved his field equations to get this answer. It wasn't. That continued their greatest mistake. Arguments about the validity of Einstein's work or the accuracy of his field equations have been going on for decades. But the easiest way to resolve the argument is to solve Einstein's gravity theory from within his 1916 Foundations paper. Using early undergraduate mathematics will make it easy to understand. To do so, you do not need to know or use his field equations. You can start at any point he used before he derived them. That way, if he made a mistake later on, the solution will still accurately reflect his theory. The best place to start is with this multidimensional differential equation from section 8 of his paper. The two ds squared terms are the same. As mentioned before, the mu and nu terms are x, y, and z for the three space dimensions and t for time. The s term is the four-dimensional space-time coordinate. Filling in all the g, mu, nu terms gives this set. The like terms xx and tt are just those terms multiplied themselves. They become squared and reduced to these equations. That gives this second set of terms. There's nothing complex about that. The next step is to add the d mu and d nu terms. That gives this set of equations. This is a quick reminder from the previous slide that shows the ds squared term. The next step is to realize that when the mass is large enough to generate significant gravity, the gravity at distance r from its center of mass is symmetric. That means the x, y, and z terms are the same. They are different from the t terms. The ds squared term can then be written as shown here. Many mathematicians ignore the a to m terms because they are not needed in the derivation of the solution. So all that is needed to solve for ds squared is to read through Einstein's 1916 Foundations paper and find where he introduces the terms gx and dx as well as gt and dt and insert them into that equation. Einstein used the terms 1, 2, and 3 for the dimensions x, y, and z, and 4 for time. I use x, y, and z for spatial distance to separate it from t as time. Many equations and pages later we come across his term G44, or as he does it, GTT equals 1 minus alpha over r. The alpha term is the accepted 2gm over c squared. But you'll note that he indicates it is an approximation. I mentioned earlier that he admitted his field equations were approximation. This makes two approximations in the term GTT. On the next page, he introduces his G11 equals gx squared equals minus 1 plus alpha over r. It does not include another approximation to his earlier one. The derivation of his dx term equals 1 minus alpha over 2r is given here. Interested parties can pause here to check the accuracy of what is derived. Those steps were introduced to show Einstein used a lot of approximations. They should have been a warning to all those making exact solutions to his field equations that exact solutions to approximations were only ever approximations. It didn't. Mathematicians kept compounding their mistake. That derives the space term. Gravitational time and distance are related through each being the negative inverse of the other. That gives GTT equals 1 over 1 plus alpha over r. Einstein approximated that to G44 equals GTT equals 1 minus alpha over r, as shown here. In the same manner as before, dt becomes 1 plus alpha over 2r, and dt squared equals 1 plus alpha over r. Those approximations are only valid when alpha is much, much less than r. Alpha for the Sun is about 3 kilometers. Mercury's orbital radius is nearly 60 million kilometers. Now, they are valid approximations. I mean, it's sort of equivalent. 1 over 1 minus a millionth approximately equals 1 plus a millionth. We can now insert those terms into the ds squared equation. The x term becomes minus 1 plus alpha over r multiplied by 1 over 1 plus alpha over r equals minus 1. And you can go through the same with the other terms, just that when you get down to the t term, it is 1 over 1 plus alpha over r multiplied by 1 plus alpha over r. So you basically just get these 3 minus 1s and 1 plus 1 term. It is no coincidence that Einstein suggested early in his work that this was the format that would apply. Now, in reality, it tells us nothing except that space response is different from the time response. That brings us to what Einstein considered his greatest thought. An observer with no external reference cannot tell the difference between being accelerated in gravity-free space or being in a gravitational field. The only way of telling the difference is to fix one of them. Fixing the derivatives means fixing a point in space where Newton's g has a fixed value. Fixing them at 1 allows that result to be multiplied by that g value at that point. And so that gives this equation where you have the minus 1 plus alpha over r for the x, y, and z, and 1 over 1 plus alpha over r for time. I mean, these are the Cartesian coordinates x, y, and z, and time t is different. Converting them to spherical or polar coordinates is virtually a lookup table, or details can be found in Shawshield's 1916 paper. That then gives the answer of ds squared equals dt squared over 1 plus alpha over r minus dr squared times 1 plus alpha over r minus r squared d theta squared plus sine squared theta d phi squared. So there you have it. The accurate solution to Einstein's gravity field equations calculated from his paper in a few minutes. Yes, it is that simple. Equally simple is to attach Einstein's radial differential term to Newton's r term in his gravity equations to give Einstein's gravity GE equals gm over r squared times 1 plus alpha over r. The ds squared solutions to Einstein's gravity field equations are not the full gravity equation. They are only the difference between his space-time distortion and Newton's gravity, which is a strength of gravity when there is no space-time distortion. This shows both solutions. The derived solution used the terms Einstein derived. The accepted Schwarzschild solution incorporates the approximations Einstein used. When alpha is much less than r, they give the same answer in most situations. The sole exception is the Schwarzschild metric predicts orbital regression. The derived solution predicts orbital precession. Orbital precession is observed. The big problem came when mathematicians extended the calculations towards r equals alpha. That is what predicts black holes. It is nothing more than mathematicians extending approximations beyond their valid range. Believing those results are accurate is a huge mathematical no, never. Well, it should be. Einstein indicated he used approximations that were only accurate for alpha much less than r. It is left to those who calculated the Schwarzschild solution to explain why they did not recognize and incorporate to get the correct answer. My own impression is that most were carried away with his apparent complexity. It seems they wanted to prove that Einstein was wrong and they were right. Most people would find it difficult to understand, let alone use this solution. As shown in the last slide, all you have to do is attach the differential r squared term to Newton's r squared term to get the full strength of Einstein's gravity at GE equals gm over 1 plus alpha times r squared. It is quite accurate for all values of r greater than about 3 alpha. The same technique can be applied to the Schwarzschild metric. The full gravitational field strength at distance r from the center of mass becomes gs equals gm over 1 minus alpha over r times r squared. It is only valid for r much greater than alpha, and the only exception is that it predicts orbital regression, not precession. Compare those equations to these equations, which the experts say are exact forms of Einstein's gravity field equations. Even if mathematicians could solve them, all they would get is the difference between their interpretation of Einstein's gravity field equations and Newtonian gravity. In the meantime, a lot of students who could solve Newtonian gravity problems could solve these relativistic gravity equations. Einstein indicated Newton's inverse square law of gravity was the first approximation to his gravity field equations. Well, to me, each of these equations seems a sort of variation to Newton's inverse square law. One can only wonder why Einstein did not solve his gravity theory using these two methods mentioned earlier. Was it because he did not understand calculus, so could not expand on his 1911 paper? That could have given him the exact GR equation. Did he not understand how to rearrange the G mu nu terms? That would have given him the GE term as shown above. It would have avoided all possibility of misinterpretations. Or did he realize that if he used either of those techniques, people would realize there was nothing complex in his gravity theory? That would have left him without the aura of a superhuman mathematician. For whatever reason, Einstein's use of excessive and unnecessarily complex maths to derive his field equations gave him an aura as an almost superhuman mathematician. That was his style, so what? So he decorated his maths a lot. It's not his fault that those who tried to prove him wrong, or that they were better than them, could not recognize his superfluous equations, or the simple solutions mentioned above. Nor is it my fault that a century of those who considered themselves the world's best mathematicians or mathematical physicists did not read his 1911 and 1916 papers and recognize the underlying physics and the relatively simple maths associated with his gravity principle. A lot of people find it easier to understand a topic if they can visualize it. This slide shows an image of the four gravity field equations. The horizontal axis is the distance from the center of mass for distances outside its physical radius. It is measured in multiples of the Schwarzschild radius. The vertical axis is the gravitational field strength at that distance. To visualize it, simply use a thought experiment of rotating those curves through 180 degrees around the central vertical axis. As mentioned earlier, the solutions to either the Einstein metric or the Schwarzschild metric given by the appropriate ds squared terms of either is just the difference between the appropriate curve and Newtonian gravity curve. The redshift curve GR was derived from absolute considerations. It goes to the maximum at r equals half alpha, and it has been derived from both an integration and a differentiation. It has a very valid reason for having that shape. So here are examples of 9 different gravity field equations. They can't all be accurate. To finalize this solution to gravity, it is necessary to show which one is accurate. The 5 black on white equations are discarded because, if they can be solved, their solution only provides the difference between Newton's gravity and their solution. That leaves the colored equations. Newton's inverse square law can be discarded because it doesn't explain the observations of Mercury's perihelion, the bending of light rays by the sun, and the observed images at the center of galaxies that are said to be black holes. There are only 2 possibilities. Gravity is either stronger or weaker than Newton's inverse square. Stronger gravity predicts black holes, of which this image is considered an example. Weaker gravity predicts orbital precession, which has been observed. The solution is this redshift metric. It shows that gravity is strongest at r equals half alpha. When particles are attracted by a gravitational field, their greatest velocity will be at their highest gravitational field strength. That is where colliding particles are moving the fastest, and that is where they will emit the most radiation. This redshift gravity equation predicts there will be a torus of radiation having a maximum at r equals half alpha. The so-called black hole image has a similarity to the image predicted from the redshift gravity equation. This redshift metric predicts both orbital precession and the observed images from the galactic center. All factors, including temperature, automatically match. No assumptions are required. Black hole image requires some assumption. This requires none. Black holes are supposed to have a maximum at r equals alpha. These have a maximum at r equals half alpha. Suggestions that at 20,000 or 50 million light years, measurements can be accurate to a factor of 2 are fanciful. The only conclusion is that the redshift gravity, gr equals gm over r squared e to the alpha over r, is the actual gravity equation. It matches all known gravity situations. It has been derived independently by 2 means, one an integral, the other a differential, and it comes associated with a very valid physical reason of why gravity should operate and why it is strongest at alpha over 2. There is no reason why any mathematician or mathematical physicist after 1920 could not have solved for any of those equations. Had they done so, they would never have allowed their calculations to go so badly wrong. After all of that, what is Einstein's gravity? It is a mathematical theory, as he said it was. It is founded on Newton's gravity theory and his calculations that photon had mass. His 1911 paper allowed him to visualize how gravity worked. He tried to solve the general relativity situation of bodies accelerating with respect to each other. For that he needed tensors. It got too complex, so he reverted to a study of gravity, its only useful application. Einstein used his visualization as a guide to make his way through his gravity equations. That enabled him to say his gravity theory originated from his general relativity work. It derived the correct answer for the bending of light rays by the sun at the end of all his complex maths. He introduced the idea that gravity was caused by mass distorting space-time. He never indicated what space-time or its distortion were physically. His complex field equations are shown in these black-on-white equations. That led others to try to solve them. They did not understand the physics that underpinned them. If they did, they would have solved and got the GE equation. Or if they had simply integrated Einstein's 1911 paper on gravitation and light, they would have derived this exact equation. None did. That is why they drifted off to make such a huge mathematical mistake. The next episode shows how that drift led to their huge mistake. Ladies and gentlemen, welcome to my second episode on Mathematicians' Greatest Mistakes. Episode 1 of this series showed Einstein's gravity field equations were only approximations that solved for the difference between his theory and Newton's gravity. It also derived the full gravitational field equations for Einstein's gravity and the exact equations for gravity. This episode shows how that exact gravity solution blows up the Big Bang theory. It explains how an infinite steady-state universe fits astronomers' observations much better. By the early 20th century, astronomers knew the universe was much larger than our own Milky Way. They had observed other island universes, now called galaxies. Being unable to solve the mystique of Einstein's gravity, the only gravity equations they had were Newton's gravity and the Schwarzschild metric. The use of Newton's gravity played a big role in the development of the Big Bang theory. The main use of the Schwarzschild metric was to say that many observations of unknown origin could be due to black holes. And without these equations, they were working in the dark. First thoughts were that the universe was infinite and steady state. Problems were soon realized. In his shell theorem, Newton indicated the gravitational field of a body of uniform mass distribution could be treated as if gravity originated at the center of mass. Laplace and Poisson extended that to a uniform mass distribution of particles, making it entirely useful in the studies of the universe. So within the vast universe, any point can be regarded as the origins of gravity of a theoretical sphere of any radius. The mass m of galaxies in radius r is given by m equals 4/3 pi r cubed rho, where rho is the density. Newton's gravitational attraction, just gn equals gm over r squared. Inserting m gives gn equals 4/3 pi r cubed rho g over r squared. Reducing the r's gives a single r on top, so as r tends to infinity, Newton's gravity tends to infinity, and thus, under Newton's gravity, an infinite steady-state universe will collapse. But what happens when we use Einstein's gravity? Well, this is his gravity field equation, 4/3 pi r cubed rho g over 3 r squared times 1 plus alpha, where alpha equals 2gm over c squared. When we insert that, we still have the r cubed over r squared, so that becomes r1. But we have here 1 plus an r cubed term over an r term, so this gives a single r distance in the top line and an r squared term in the bottom line. So as the radius, the distance tends to infinity, Einstein's gravity tends to 0. So, under Einstein's gravity, an infinite steady-state universe will not collapse. Before we follow the mathematicians' trail, it's worth looking at what the universe would look like under the redshift metric and the Schwarzschild metric. Under the redshift gravity, you have gr equals gm over r squared e to the alpha over r. Inserting alpha again gives you a term with an r cubed on the top and an r squared on the bottom, and then you have an exponential of an r squared term because the r on the bottom diminishes that to r squared. So as r tends to infinity, gr tends to 0 and quite rapidly. So an infinite steady-state universe will not collapse. Under the Schwarzschild metric, we have gs equals gm over r squared 1 minus alpha over r. That becomes this term where you can see that although there is an r squared, it's subtracted away. So when 8 pi g r squared rho equals c squared, gs equals infinity. Using rho equals 10 to the minus 26 kilograms per meter cubed, which is about the density of the universe, gives gs equals infinity at r equals 10 to the 10th light years. So under the accepted Schwarzschild solution, an infinite steady-state universe would have long ago collapsed into centers of about 2 times 10 to the 10th light years apart. Or under the Big Bang theory, it had happened more recently, and we should be seeing photons from distant galaxies being blue shifted. Neither of these events has occurred. Look, just forget the Schwarzschild metric. It has nothing going for it. It was calculated by people who could not understand the simple approximations Einstein said he made. There is no physics to support it. It predicts orbital regression when only orbital precession has been observed. Predicts the universe can't exist. Had mathematicians worked that out, they should have realized something was wrong. They could have avoided their biggest mistake. They didn't. It is worse than that. Mathematicians and mathematical physics have been working for decades using mathematics without knowing its physical basis. That is another big no, never in the real physical world. It is a huge contributor to their greatest mistake. Mathematics does not make things happen. Perhaps they thought because Einstein said he used purely mathematics approach to obtain valid results, they could do the same. However, their collective efforts have resulted in their needing 24 times 10 to the 60 times as much mass energy as astronomers observe to explain their observations. I'm not sure if Einstein was aware that the solution to his field equations predicted that his gravity was weak of an inverse square in such a way that an infinite steady-state universe would not collapse. In any event, this extract from his 1917 paper on cosmological considerations shows he considered only a finite universe. Such a universe will collapse under any gravity theory. He introduced his cosmological constant to prevent that from happening. In 1929, Edwin Hubble observed that the more distant galaxies were the greater was the redshift of photons from them. That caused Einstein to admit his cosmological constant was the biggest blunder of his otherwise great career. That was the start of the Big Bang theory. The Belgian priest Lemaitre is credited as being the first person to suggest the universe started from a primitive atom. The issue of black holes is only a minor irritation in the overall scheme of mathematicians' greatest mistakes. The Big Bang theory has its detractors, but its supporters insist they have the mathematics and observation on their side. It is hard to argue against maths that nobody understands. It persists because observations, as proponents say, can only be explained by an expanding universe theory. Under that theory, these features keep recurring. Gravity is only attractive, so an infinite steady-state universe would collapse. The observed photon redshift increasing with distance has no other valid explanation. All tired light theories, their possibility proposed by Wiki, were debunked. Tired light explanations could not explain the observed time dilation of type 1a supernovae that increased linearly with redshift. A mechanism for slowing light requires scattering by particles, which would blur distant images. Tired light theories could not explain the observed cosmic microwave background radiation. Tired light from a steady-state universe could not pass the Tolman test. In an infinite universe, all the hydrogen would have long since fused to helium, and there would be none left for stars to fuse. Entropy always increases. After infinite time, the universe should have infinite entropy and died a heat death. Element abundances are approximately the same as calculated from Big Bang nuclear synthesis. It is time to consider each of these in turn. Gravity is only attractive, so an infinite steady-state universe would collapse. Well, as was shown earlier and repeated here, an infinite steady-state universe will collapse under Newtonian gravity. Einstein's gravity showed that as r tends to infinity, gr tends to 0, an infinite steady-state universe will not collapse. The same occurs under the redshift gravity equation. R tends to infinity, gr tends to 0. All evidence is that the redshift gravity gr applies in all situations, so an infinite steady-state universe will not collapse. So to show how this works, I'm going to use this illustration. It consists of these circles representing, let's say, a visible universe of, say, a radius of 10 to the 10th light years, where x in the middle of visible universe A. Newton's shell theorem applies to all forms of gravity. The strength of gravitational attraction at the boundaries of this, under the redshift gravity, will be about 5 times 10 to the minus 12 meters per second squared. As that goes out, it gets larger, 10 to the minus 13, 10 to the minus 15, approximately 10 to the minus 18 meters per second squared. Now, to show what is happening, we'll just consider that a visible universes D and E have no gravitational attraction on each other. So our visible universe A would attract C and B towards it. However, infinite universe E will attract C towards it, and the same as D will attract B towards it as well. So that prevents those collapsing in on A. This effect goes in all 3 dimensions and forever in an infinite universe. And the same effect occurs under Einstein's gravity as well. So the infinite universe will not collapse under gravity. That ends the requirement for the 10 to the 60 parallel universes in any dimensions. I mean, that's it. End of story. No further argument should be considered. The next point is the observed photon redshift increasing with distance had no other valid explanation. All tired light theories, their possibility proposed by Zwicky, were debunked. Over the decades, dozens of theories have been proposed for its origins. Marmot evaluated all he could and found none were valid. But it has been known for some time that most detected cosmic rays originate within our galaxy. It was explained as them being slowed down by the intergalactic cosmic microwave background photons. Something similar to photons, but far more numerous, are cosmological neutrinos. If you have a look at those figures, they are very large compared to these. They have a rest mass of about 10 to the minus 4 eV per c squared, and that actually shows up, that's 10 to the minus 6, 10 to the minus 3, that's about 10 to the minus 4. Several other experimental observations that indicate neutrinos have a rest mass of about 10 to the minus 4 eV c squared. And look, despite what the standard model doesn't tell us about them, neutrinos are rotating plane polarized photons with that rest mass of about 10 to the minus 4 eV per c squared. That gives them a diameter of a few millimeters and a temperature equivalent of about 1.5 degrees K compared to cosmic microwave background photons of about 2.7 degrees K. Being electromagnetic radiation, they have the same effect as that attributed to cosmic background photons. There are so many of them that they provide a continuum throughout the universe. That continuum provides space with a property called viscosity. It slows down objects according to their momentum p, but does not scatter them. If Marmot or others studied it, they would find the following. I won't go into the maths, just give the details. The momentum loss for things electromagnetic is given by delta P equals 1 plus h naught over c to the d minus 1, where h naught is Hubble's constant and d is distance. Photons are constant velocity particles. Their speed is determined by the electric permittivity of matter-free space. That means their momentum loss becomes their redshift. So photon redshift is given by z equals 1.0000715 to the d minus 1. D is distance in million light years. The H naught and D figures come from the work of Friedman. As an approximate guide, a photon has to travel through about 10 to the 27 neutrinos for each million light years it travels through intergalactic space. That causes it to lose 0.00715% of its starting momentum. That is not considered excessive. It will be shown later that it is supported by other observations. So the greater the distance photons travel, the greater will be their redshift. With no scattering, it has all the properties needed to explain observed photon effects. This equation was used to calculate the viscosity versus redshift under the mechanism just described. It gives this V-curve. Superimposed upon it is the Doppler redshift curve. They're about the same up to redshift around about 0.8 on this scale. But the thing to note, redshift 5, it's about 12.2 billion light years. Here you're talking about 25 billion light years. So no matter how far telescopes peer into space, they will always detect fully formed galaxy images. And you'll see here the Hubble Ultra Deep Field and Webb's first deep field images. They're all fully formed. Rather than reconsider their options, mathematicians try to use more maths to explain what should now be obvious. The universe is infinite. They keep scrambling for new equations to match new observations. All the scrambling in the world won't match with physical observations. It has only succeeded in compounding their greatest mistakes. These images are strong indications the viscosity redshift theory is real. More on that later. This neutrino viscosity effect on photon redshift is supported, not debunked, by observations. Next we come to tired light theories could not explain the observed time dilation of type 1a supernovae that increased linearly with redshift. Well, redshift depends upon the photon's momentum. Blue photons, energy 4 eV, have twice the momentum of red photons, energy 2 eV. Red photons will take longer to be redshifted through any value than blue photons. For z equals 1, they will be spread out over twice the time than for local SNE 1A spectra. And that's what Goldhaber et al. Observed. Next we come to a mechanism for slowing light requires scattering by particles which would blur distant objects. There were redshift proposals that involved photons being slowed down by interaction with intergalactic particles such as protons and electrons. That redshift mechanism could generate the observed redshift, but it would blur the images. Neutrinos are different. They are rotating plane polarized photons with rest dimensions of the order of a few millimeters. Their electromagnetic field is exceedingly weak. They exist in such huge numbers they provide a continuum in space that gives it the viscosity that redshifts photons, and it does that without scattering them. It will be shown later this viscosity effect is very real. Next we come to tired light theories could not explain the observed cosmic microwave background radiation. In 1926, Eddington calculated the background temperature of space based on photon emissions as 3.18 degrees K. In 1933, Regner predicted it as 2.8 degrees K. Both were made for an infinite steady-state universe. Calculations from Big Bang proponents were between 5 degrees K and 28 degrees K, as long as we excluded Gamow's 50 degrees K in 1948. Later discovered by Penzias and Wilson in 1965 and measured as 2.718 degrees K, mathematicians modified their calculations to match their theory to observation. Cosmic wave background has nothing to do with the Big Bang and expanding universe theory. It is simply the background temperature of space associated with an infinite steady-state universe. It was calculated over 30 years before it was discovered. Then we come to tired light from a steady-state universe could not pass the Tolman test. Tolman was optimistic about the magnitude expected from receding galaxies and pessimistic about that from a steady-state universe. In any event, this mechanism passes the Tolman test, so that's not a problem. For the record, if we applied this equation to 1 GeV photons, the typical cosmic ray energy, we get this result. After traveling 10 to the 4 light years, which is pretty much local within a galaxy, they've only lost 0.5% of their momentum. By the time they've traveled 10 to the 5th light years, which is basically across a galaxy, they've lost 5% of their momentum. By the time they've traveled to the nearest galaxy, which is typically 10 to the 6 light years away, they've lost 30% of their momentum. And then by the time they've tossed the equivalent of 10 intergalactic distances, there's virtually nothing left. So this effect explains why very few cosmic rays originate from outside our galaxy. That is enough about the so-called tired light problems. The neutrino viscosity mechanism passes them all. I mentioned earlier I would have more to say on them later. That later is now. Calculations of Mercury's perihelion precession predict it would be 43 arcseconds per century. Measurements by Park et al. Show it is more like 41.8 arcseconds per century. It's difficult to be highly accurate because Mercury and Earth keep changing their position relative to each other and to the background stars. To explain what could slow down Mercury's orbital speed, we'll apply that same equation to a nucleon of mass 938 MeV per c squared and is travelling at Mercury's orbital speed. From that we get a nucleon would be slowed down by about 1.6 arcseconds per century to about 41.4 arcseconds per century. Now, this effect applies equally to all Mercury's nucleons because they are all exposed equally to the same neutrino density. Neutrinos are ever present everywhere, penetrating empty space and mass equally. Cosmic microwave photons can't penetrate mass. They do not contribute to this effect. It slows Mercury's orbital precession from 43 arcseconds per century to 41.4 arcseconds per century. However, neutrinos have mass and will be attracted by the Sun's larger mass. The density of cosmological neutrinos would be less near the Sun than in intergalactic space. That would reduce the viscosity effect on Mercury, making it closer to the observed precession of about 41.8 arcseconds per century. That agreement is considered reasonable. It gives further indication of the existence of this effect. There are other observations that suggest this effect is very real. They are seen in these images of spiral arm galaxies. Feature they all have in common is that the spiral arms lag behind their galactic core's rotation direction. Many thousands of them have been imaged. Now, that is a clear indication there is something causing that lag. Suggestions that stars with masses of 10 to the 55 or 10 to the 60 nucleons could be slowed down by background photons or cosmic rays are just not realistic. That leaves neutrino viscosity as the most obvious explanation of that lag. It causes the reduction in Mercury's orbital precession, the slowing down of cosmic rays, and the redshift of photons from distant galaxies. Spiral arm rotation is slowed down by the nature of cosmic neutrinos, giving space its property called viscosity. This has shown the effect is very real, very large, and very universal. Next we come to, in an infinite universe, all the hydrogen would have long since fused to helium. There would be nothing left to fuse, and, point 8, entropy always increases. After infinite time, the universe should have infinite entropy and have died a heat death. Neither of these have happened. The reason is the same for both. Gravity reverses entropy. That is usually indicated to be wrong because of the second law of thermodynamics. And a quick question. Which is more disordered? A large gas and dust cloud, a few light years in diameter, or its collapsed form of the Sun and planets neatly orbiting in our solar system? Well, the mathematicians will say, well, that doesn't consider the bigger picture of photons emitted and the higher speeds of the hotter particles. It is they who are missing the bigger picture, which I will now show. To understand it, you must go back to the theory of gravity. This redshift gravity equation is the only one that predicts this shape because of the maxima at r equals half alpha. And there is very sound physical reasons for gravity to be strongest at radius of half alpha, which could be outside the radius of a massive body. And compare that to black holes. They have no physical reason for existing. Their mathematical reason is because mathematicians made multiple mistakes. Gravity is only attractive. For something as massive as the Sun, the Schwarzschild radius is about 3 kilometers in a physical radius of about 700,000 kilometers. The Schwarzschild radius increases linearly with mass, while the physical radius increases by the cube root of mass for the same material. With enough mass, a stage will be reached when the Schwarzschild radius is outside the physical radius. That would only occur for neutron stars. Now, the gravity inside neutron stars doesn't just attract protons, electrons, and neutrons. It also attracts photons and neutrinos, taking their entropy with them. Under the huge gravitational force, photons are incorporated into the mass of the neutrons. Neutrinos are absorbed when gravity forces an electron into a proton. That takes away 0.8 MeV energy for each conversion. Contrary to the mathematicians' standard model, neutrons are not made up from quarks and gluons. They've never been detected anyway. They have a structure that can be compressed but will not collapse. It is one in which their magnetic poles will align in their direction of travel, and they also orient themselves so that the south pole of one is adjoined to the north pole of another. So all neutron stars rotate. Almost all neutrons will be aligned in such a fashion. When the diameter of a neutron star is many kilometers, the diameter of a neutron is about a femtometer. Neutrons adopt this structure. It provides a wonderfully strong structure throughout most of the neutron star. Everything is neatly ordered in the most condensed state possible. It is hard to visualize anything that has a lower energy per unit mass than a neutron star. That's the big picture of which mathematicians are unaware. Close to the center of a rotating neutron star can't get an ordered pattern. Around the central axis you have this weaker structure. Structure is of course weakest at the surface. As these gravity redshift curves show, gravity is stronger on the outside than on the inside. This means that the strong external gravity will be pulling the neutrons towards the outside, leaving the center somewhat less dense. A stage is reached when neutrons in the center are no longer being compressed by gravity. The electrons that were forced into protons to form neutrons are free to escape from neutrinos. They form hydrogen atoms which become molecules. Every time a neutron changes to a hydrogen atom, it releases 0.8 MeV energy. Passage of time sees more hydrogen gas produced. The pressure and temperature become so high, some fuse into other low Z nuclei like helium. But ultimately a stage is reached where the internal pressure is so high the gas breaks out at the weakest point, and that is the center of rotation of the neutron star. So out comes this narrow stream, mostly hydrogen, but a bit of helium and the occasional low Z metals. It is accompanied by lots of photons. As well as the high pressure, they are also accelerated by the gravity field being outside the star. Usually just one pole erupts and you get one jet, but occasionally both poles can break at once and you get two jets. Now each hydrogen atom that comes out is also accompanied by up to 0.8 MeV. That is a lot of energy to be released with particles and photons flowing out in a narrow beam through a long, narrow cylinder in the center of the neutron star. These objects are known as quasars. They both reverse entropy and change material primarily back to hydrogen. Their large number of nucleons means they can keep emitting particles and large amounts of energy from a long, small diameter cylinder for a very long time. The process from one quasar emission through gas and dust cloud condensation to form stars and planets that make their way through to the center of a galaxy to be cycled again may take hundreds of billions of Earth years. So what? An infinite universe has all the time in the universe. So that is how gravity reverses entropy and recycles matter back to hydrogen. That mechanism keeps the universe going forever. Cosmologists attribute quasars to an extra-large black hole swallowing up so much matter that very hot regions emit large amounts of energy. And that requires many improbable assumptions. This explanation is straightforward, no other assumptions required. Another feature is that the redshift is equal to e to the alpha over t 2d, which approximates to this, which means it has a mass in the top line. A large mass can give a high gravitational field. Quasars with observed high redshift do not mean they are distant objects that were features of the early universe. It means they can be massive objects that have a high gravitational redshift and are close. They are an integral part of the functioning infinite steady-state universe. Now we come to element abundances are approximately the same as calculated from Big Bang nuclear synthesis. Mathematical modeling of element formation after the Big Bang shows that there would only be enough energy density to fuse protons into helium and maybe the occasional lithium nucleus. That ratio would be about 88% hydrogen and 12% helium by atom numbers. Approximately the same numbers are found in cosmic rays and quasar emissions. They are the mechanisms by which matter is recycled in an infinite steady-state universe. That the great majority of the universe is composed of hydrogen and helium, with about 1% of it being made up of the heavier elements, is what is expected in an infinite steady-state universe. After that, there is nothing left for Big Bang theorists to hang on to. Their mathematics has nothing to support it from Einstein's work. The features they say could only originate from an expanding universe have been debunked. The Big Bang theory has many problems it can't explain. What was the nature of the infinitely dense singularity from which it started? Why is the universe's expansion so evenly balanced at 1 in 10 to the 60 probability? Why are fully formed galaxies still seen when the James Webb Telescope images were supposed to come from so close to what should have been the early universe? And there are many, many others. Surely it is time for mathematicians realize that a probability of 1 in 10 to the 60 chances of the universe existing equates physically to 0. There are those who would like to question the above findings because the neutrons and neutrinos were not as presented in the Standard Model paradigm. They insist the Standard Model is the most accurate model ever developed. Well, the Standard Model was developed by mathematicians. Its accuracy was confirmed by other mathematicians. An analysis of its physical meaning show it has far more physical unknowns than it has mathematical answers. The neutron and neutrino model I used is part of a model that describes the known stable particles, their properties. It shows how the structure of each particle is responsible for its properties such as mass, the special relativity corrections, electric charge, spin, chirality, and more. As presented earlier, it also solves many cosmological issues. This physical-based model works. People like Galileo, Newton, Faraday, Planck, Einstein, Dirac, Feynman, and others used mathematics and made great progress. The Big Bang and expanding universe theory was likewise based on mathematics. So why did it go so wrong? Well, Paul Dirac once wrote, "It is more important to have beauty in one's equation than to have them fit experiment, because the discrepancy may be due to minor features that are not properly taken into account and that will get cleared up with further developments of the theory." It seems that if one is working from a point of view of getting beauty in one's equations, and if one has really a sound insight, one is on a sure line of progress. A sound insight is an understanding of the physical principles that underpin the mathematics. It seems the mathematicians were too wrapped up in what they considered the beauty of Einstein's equations to worry about the physical principle upon which they were built. So collectively, that has blown up the Big Bang theory. It was introduced because early mathematicians could not understand the simplicity of Einstein's gravity. The physical reality, as supported by the aforementioned physics and maths, is that the universe is infinite in space and time. In intergalactic space, those dimensions are Euclidean. The gravity of galactic, stellar, and planetary masses changes that slightly when close to them. Occasionally they pass by a massive object to form an Einstein cross. Some may be deflected as they pass a massive object. Otherwise they will travel vast distances in straight line through Euclidean space, and as shown before, as they make their way they are simply redshifted. Beyond that, two effects prevent astronomers from seeing forever into space. One is the neutrino-induced viscosity of space that slowly redshifts photons until they merge into the cosmic microwave background. The other is the collective gravity of galaxies when photons travel, say, 50 billion light years. It increases photon redshift beyond the viscosity reduction. Now, those who care about what is happening 50 billion light years away can calculate how much gravity contributes to photon redshift. It's not a difficult calculation. The infinite steady-state universe has a 100% chance of existing as observed. The next episode deals with the proposed dark energy and dark matter cosmologists need to explain astronomers' results. Ladies and gentlemen, welcome to the third episode of my presentation on mathematicians' greatest mistakes. In the first episode, I showed just how easy it was to understand the physics of Einstein's gravity equations and solve them. And they were only approximations anyway. So I also showed how easy it was to derive the exact solution to gravity. In the second episode, I removed the 1 in 10 to the 60 odds of the universe existing. The universe is infinite and steady state with a 100% chance of always existing. Observations that were thought to be exclusive to the expanding universe were shown to have simple physical explanations. They were supported by mathematics and observations. There are still the issues of the 73% dark energy and 23% dark matter that mathematicians require to match astronomers' observations and measurements. Dark energy is required to cause the universe's expansion to accelerate. Dark matter is required to match the observed rotation speeds of galaxies. But if the universe is not expanding, why should we be concerned about its accelerated expansion? Well, the results were obtained, so we need to evaluate them and find out what their measurements mean. Figure A is the reason mathematicians think they need dark energy. It is a plot of the measured magnitudes of type 1a supernovae, hereinafter referred to as SNE 1a, and at different redshifts. SNE 1a are a particular type of exploding star. They are not easily confused with other celestial events. The magnitude of an astronomical light source is a measure of the intensity of its light between wavelengths of 300 nanometers and 900 nanometers. It is not the total intensity of all detected light. Magnitude is an inverse logarithm relationship. The dimmer is the measured intensity of the higher is its magnitude. A star with a brightness 1% of that of another star has a magnitude 5 times higher than the brighter star. Determining magnitude under the expanding universe theory worked on the principle that light from distant objects would be redshifted both by the distance to the observer and the speed at which they were moving away. Curve D is the calculated intensity expected from SNE 1a at the distance determined from the Doppler redshift equation. It does not include the intensity loss due to its motion of moving. Curve E is the intensity expected from SNE 1a receding from us as observers. It includes curve D. Both present the intensity of all the light. Line A is what the mathematicians were expecting to see if the universe was expanding at a constant rate after the Big Bang. It is sufficiently close to curve E not to make a significant difference to the outcome. Figure B is a typical SNE 1a spectrum at emission. The vertical axis is relative irradiance, a scientific term for intensity. The horizontal axis is wavelength. It's measured in nanometers. SNE 1a emit very little radiation at wavelengths below about 330 nanometers. The curved line is the intensity if the photons were emitted in equal numbers at all wavelengths. Figure C shows what happens when a spectrum is redshifted through different amounts. The overall intensity is reduced and the amount of the spectrum under 900 nanometers diminishes. At zero redshift, all the spectrum in B is detected and is included in its magnitude measurement. At redshift 1, the blue curve, its intensity has halved and only a small amount of the spectrum is measured in that magnitude range below 900 nanometers. Beyond redshift 1.5, there is almost nothing left to measure. Its magnitude goes very high very quickly. The actual measurement process reduces the magnitude below the calculated intensity. Curve F is what is calculated when the light from the Doppler redshifted SNE 1a has been measured for magnitude. Personally, I believe curve F is within the error range of the measured magnitude at different redshifts. So under the expanding universe model, it indicates the universe was either expanding at a constant rate or perhaps slowing down a little bit. But there is nothing in it to indicate the universe's expansion has accelerated. The earlier episode showed the universe was not expanding. We now need to check what those measurements mean in an infinite steady-state universe. Figure A is a quick reminder of the different distances attributed to the Doppler and viscosity redshift measurements. Figure B shows the difference between the two curves up to redshift z equals 1. Now, the D and V curves start to separate at redshift approximately 0.4. On graph C, the vertical axis is the expected SNE 1A magnitudes at different redshifts, shown on the horizontal axis. Curve V is the intensity expected from SNE 1A spectra being redshift by the viscosity effect for their distance. It is determined from the V curve in figure B. This inset is a reminder that the magnitude differs from intensity because their spectra move through the measurable range from 300 to 900 nanometers. Add that magnitude correction to curve V and you get curve J. Between you and me, I think J is a reasonably good fit with the observed SNE 1A magnitudes at different redshifts. Curve J applies for a universe that has a 100% chance of existing forever. Curve F applies for a universe that has a 1 in 10 to the 60 chances of existing now. Your choice. The astronomers who measured those magnitudes at different redshifts did a good job. What they measured was the SNE 1A magnitudes expected from an infinite steady-state universe. It was the mathematicians who interpreted it as requiring dark energy equivalent to 17 times the observed mass energy of the universe to give the universe a 1 in 10 to the 60 chance of existing. Is it possible that the whole suggestion about dark energy was due to mathematicians not adding the magnitude correction factor when they calculated the expected magnitudes at different supernovae? Perhaps all they calculated was the expected intensity. That is left for them to explain. Curve J and its calculations show there is no dark energy. The universe is not even expanding, let alone expanding at an accelerating rate. That gets rid of dark energy. It still leaves dark matter. It was predicted from galaxy rotation. The pinwheel galaxy shown is typical of spiral arm galaxies. Galaxies rotate for the same reasons as planets rotate around the sun. The material from which they were formed did not move radially into the center. Their rotation minimizes gravity collapsing them into their center. Astronomers measured the speed at which different parts of the galaxy rotated. The results are shown plotted in figure A. Theoreticians did not have a good theory for galaxy rotation. They used a variation of Kepler's law of planetary rotation. It predicts rotation should be somewhat as shown in figure B, a rapid increase in speed away from the center to a maximum. That is followed by a decline from maximum speed at greater distances. Well, the astronomers' measurements showed the initial rapid speed increase. At greater distance, the speed did not decrease very much, if at all. The only thing mathematicians could think of was that there was some other form of mass that affected galaxy rotation, but did not have any other effect. They called it dark matter and sent astronomers and particle physicists on wild goose chases for over 50 years to search for it. Planetary motion differs from galaxy motion in important ways. Planetary motion is about a large central mass, the Sun. It contains about 98% of the solar system's mass. Galaxy motion has mass distributed throughout it. To some extent, that can be overcome by using Newton's shell theorem. It states that the gravity of a body of uniform density acts as if all the mass was concentrated at its center, O. Well, a big problem with that is that mass is not uniformly distributed throughout a galaxy. The mathematicians were using a theory to predict dark matter that was not correct. The correct theory is to use Newtonian gravity effects for every star in a galaxy on every other star. Newtonian gravity is used because relativistic effects are too small to make a difference. A team of Sipols and the Pavloviches has done that as an approximation. They divided galaxies into segments as shown in this image of the pinwheel galaxy. The intensity of each segment was deemed to be proportional to the mass of that segment. They used a computer to calculate the effect of gravity generated by every segment on the mass of every other segment. The results are shown on the right. In these plots, the vertical scale is speed in kilometers per second. The horizontal scale is distance from the rotation center in kiloparsecs. A kiloparsec is 3.26 light years. The blue circles represent measured points. The red line is the calculated fit. The green dashed line shows the relative mass compared to the maximum mass for that galaxy. The overall agreement in this selection is good. They did this for a couple of hundred galaxies. Their fit has been similar to those for about 2/3 of them. No two galaxies are the same. A one theory fits all is not a reality. I suggest those results are a reasonable indication that galaxy rotations are somewhat as expected from gravity considerations of the mass distribution within the galaxy. No dark matter is required. There is one other physical effect that can influence galaxy properties, including their rotation. About 85 plus or minus 10% of the stars in a galaxy are outside the galactic core. Galaxies have a magnetic field that is strongest in the galactic plane and along their spiral arms. Most supernovae occur outside the galactic core. Cosmic rays from supernovae travel along the magnetic fields. Being more massive than electrons, cosmic ray protons make their way into a galaxy's core faster than cosmic ray electrons. This results in a positive charge accumulation in the galactic core, where they are captured by the stars and the small gas and dust molecules. Stars, like our Sun, emit excess protons. They either remain as protons or are captured by gas and dust molecules. This graph shows the cosmic ray flux is highest at about 1 GeV. A significant flux still exists at 10 GeV. Those cosmic rays will keep entering the central core until its voltage gets so high it stops high-energy particles from entering. As this cosmic ray energy curve shows, that could be up to around 10 GeV. The other limiting factor is the arrival of electrons that neutralize their charge. Voltages are relative. The whole galactic central core at 1 GeV or above provides two results. The stars and planets will all be surrounded by a field of the same voltage. They will experience a repulsion from other positively charged particles. They will not have an internal voltage that would blow individual stars apart. This effect has been demonstrated as shown in this Fermi decades of gamma ray discovery image. Red indicates about 1 GeV gamma rays. The brighter the color, the greater the energy and intensity of gamma rays. The brightest region is in the galactic core, shown in white. That is where the mass density is the highest. The spiral arms have lesser energies and intensities. There are almost no gamma rays outside the galactic plane. There is no solid surface holding the protons in place. They and positively charged molecules and dust particles will be repelled. There are two directions in which repelled particles will travel. They can move vertically away from the galactic plane, or they will travel horizontally along the galactic magnetic field. Not many move diagonally away from the galactic core. Its positive charge and that of the galactic plane pushes them perpendicularly away. Gas and dust particles moving vertically outside the galactic core attract electrons, neutralizing their charge. That gives a stream of dust particles moving away from the center and back to the galactic plane. Protons move faster. They escape further from the galactic plane before they too are neutralized by electrons. That gives these Fermi bubbles. In another effect, protons will also be repelled along the galactic plane. They are held in it by its magnetic field. Incoming electrons will collide with some of them. Their lower energies away from the central core means X-rays are emitted, and that is why X-rays are randomly detected with no apparent source. There are other effects this explains that are related to individual stars, but there are two that are related to galaxies. Galaxies have their greatest mass density in their central core. If gravity was the only factor affecting their mass distribution, the stars would collapse to form a small, dense core, as suggested here in A. The reality is shown in B, that galaxies bulge out in their central core. That is a strong indication that gravity is overridden by something. Positive charge repulsion induced by the capture of protons in their central core seems the only feasible alternative. Galaxies have net neutral charge. Any that had a significant net positive electric charge would soon blow apart from their like charge repulsion. A positive charge in the galactic centers means a negative charge in their outer regions. Opposing electric charges gives an inverse square law of attraction, the same as gravity. It is not that electrons accumulate on stars, they don't. They accumulate in the galaxy's magnetic field. The magnetic field drags stars with them. That may seem fanciful to some, but I draw your attention to these two galaxies, Sombrero and UGC 12591. Their most obvious common feature is their stars extend way beyond their galactic plane. Their second feature is their outer reaches rotate at over 500 kilometers per second. That is almost double that of the Milky Way and most other galaxies. There is no physical mechanism by which dark matter could account for both the huge star bulge away from the galactic plane and their high rotational speeds of the outer stars in those galaxies. This description requires a period of high supernova activity to generate the charge effect described. The above indicates one galactic rotation theory does not cover all galaxies. More importantly, it shows that galaxy rotations are approximately as expected. There is neither a need for dark matter nor anywhere for it to fit within the observed universe. Quoting Sipols and Pavlovich, perhaps dark matter is like Confucius' black cat, hard to find in a dark room, especially if there is no cat. In summary, Figure A is the mathematicians' universe. Under favorably selected mathematics, its odds of existing are 1 in 10 to the 60. The mathematicians' solutions included inventing another 10 to the 60 universes in undetected parallel dimensions. A mistake that is out by 10 to the 60 times the mass of the observed universe is about as bad as it can get. Figure B is the astronomer's universe. It is what they observe and measure. The earlier presentation used only 3 space dimensions and time, along with known physical principles and simple mathematics, to show that is all that is needed to explain known astronomers' observations. In the 19th century and earlier, classical mechanics worked well. The mathematics was relatively easy to follow. That changed early in the 20th century. The maths became a lot more complex. However, it need not have been. The apparently complex maths of Einstein's gravity field equations could have been easily solved by alert mathematicians. Here are 2 examples of how easily it was done. One involved a simple rearrangement and integrate terms from Einstein's 1911 paper. It gives the redshift gravitational field strength. The second involved going from this ds squared equation to this solution. It was done in a few slides in the first episode. That shows how Einstein, or any reasonable mathematician, could have done it. The strange feature is that many seem not to recognize that any ds squared solution was the difference between Einstein's theory and Newton's inverse square law. The full solution to Einstein's gravity is given in this GE term. Both of these solutions used classical concepts to calculate what are called relativistic gravity effects. Had mathematicians recognized that simplicity, they should not have made the 1 in 10 to the 60 part of their greatest mistake. Toward the end of the 20th century, complex maths was considered essential for cutting-edge physics. Complex maths are a problem when the physics they purport to describe is not presented. Very often, there was no physics to support their calculations. They are what led to the mathematicians' greatest mistake. Mathematics without a physical reason is now an accepted norm in many aspects of modern physics. Fortunately, it is mainly of theoretical interest. As mentioned earlier, the mathematicians responsible for that regarded themselves as the elite, the best of the best. They have definitely set the best record for the biggest mathematical mistake imaginable. This is a reminder of what can happen when mathematics is used incorrectly. With no understanding of the physics involved, they calculated the mathematical odds of the universe existing in its observed state 13.8 billion years after the Big Bang were 1 in 10 to the 60. They considered it was based on the genius of Einstein's work. Even if it didn't seem right, the universe existed, so it must be correct. Other mathematicians offered excuses as to why it could still be correct. One included there must be 10 to the 60 other universes in parallel dimensions that could not be detected. That has no physical foundation. It is not the way mathematics should be used. It seems the mathematicians were too interested in Dirac's mathematical beauty than the sound insight that supported them. The result is the world's best mathematicians claiming the whole universe as 1 in 10 to the 60 chances of existing is reasonable odds. After all, that is what their mathematics tells them, so it must be right. That sums up the lack of reality of mathematical calculations made without a physical basis. An unfortunate result is that some other mathematicians have used the complexity or secrecy of their calculations to insist the results of their work must be correct. Is it too much to ask them to show the physical basis upon which their calculations were made? The former is a one-off. That raises an interesting question. Is the mathematician's biggest mistake deriving the Big Bang theory with its impossible odds? Or is it the use of mathematics without a physical basis that allowed that huge mistake to be introduced and perpetuated? The former is a one-off. The latter can be repeated many times. It is easily avoided by physics first, mathematics second, and finish off with a common sense evaluation. That even works in the quantum world of individual particles when their structure is known. Much of what was presented in this and the two previous episodes is new to most people. Now, that's true. However, what was presented in the first episode on Einstein's gravity should have been published by 1920 or any time thereafter. That would have made it easier to find the correct interpretations of the other information presented in the second and this slide. That raises the question, why isn't this work published? Most of it has been published as part of my book, The Common Sense Universe. Interested parties can obtain copies of it from any of these addresses. It is not published in the mainstream media because journal policies require complex mathematics and that articles comply with the accepted standard model and general relativity paradigms. This book goes from the smallest subatomic particles to atoms. From atoms to stars, it acknowledges that the work done by previous physicists was the biggest contributor to humanity's doubling of life expectancy, tenfold population increase, and huge improvements in lifestyle comfort in the 300 years from 1700. That was when physicists were doing a great job. And if you don't believe me, just try living without electricity or anything generated using it. That was a physics development. The common sense universe resumes the study of gravity. From there it goes on to the study of galaxies, and it concludes with the large-scale structure of the universe. Some of that has been presented earlier. Another reason for it not being published is because of other work I have done. Part of that work involved a re-evaluation of nuclear physics. It has two noted features. It explains many phenomena that current standard model paradigms can't explain. It also suggests an alternative approach to generating electricity from nuclear fusion. That approach is based on the way fusion occurs in the sun. It matches solar fusion to an accuracy of about 3 parts in 10 to the 7. It does not need tritium, so it does not have any radioactive byproducts. All proposed principles have been independently tested and work. It is the combination that needs to be built and tested. Developing the theory and converting it to an in-principle working design, including drawings and mathematics to support the principle, is not something that can be done in a few months. The principle is scalable from megawatts to gigawatts. Building a trial megawatt reactor gives this technology a far quicker entry and cheaper price than the large-scale projects usually proposed. This study is still a theoretical development project. No guarantees can be given. However, if this fusion project does not work, it places severe restrictions on the future of other fusion work. That concludes my presentation on Mathematicians' greatest mistakes. I have shown that there are two major mistakes. The Big Bang Theory is the greatest physical mistake possible. It relied on their psychological mistake of using mathematics without a sound physical base. I have shown how a sound physical basis reduced the complexities of Einstein's gravity to simple undergraduate physics and mathematics. I have also hinted at physicists' standard model for the structure of subatomic particles. It has serious problems. One of those relates to nuclear physics. I have mentioned an alternative nuclear physics approach that is based on physical principles. It offers a strong possibility of allowing physicists to achieve their ultimate goal of generating electricity from controlled nuclear fusion. Thank you for listening to my presentation.